All right, Stats class, we're going to go over the final exam review guide that I sent out to you guys. So there's a lot of blanks on here. I just kind of want to go over the blanks and what are in those blanks. All right, just breaking down, there's 6, 7, 8, and 10 are the chapters covered here. We don't do 9 in this course, but 6 through 10 are covered with the exception of 9. So these are the different things that you're going to be doing in there. So in chapter 6, we learned to use normal CDF or normal DIST, depending on the technology you're using, to find normal probabilities. And we used inverse normal or norm.inv on the spreadsheets to find numbers that had an area to the left or to the right of them. So for example, on this problem, there's an area to the right of 0.0918. So I could use second vars inverse normal, and the area is always the area to the left, so I would do 1 minus the area to the right. So 0.0918 is the area to the right, 18, and the area to the left is 1 minus that. Okay, the mean is 0, the standard deviation is 1 because this is the z distribution. All right, and so there would be that number, 1.33 roughly is that number that cuts off that upper area of 0.0918 from the lower area. All right, you can do that with norm.inv with Sheets Excel the same way. You would have to subtract the area from 1 because it's an area to the right. All right, same thing for percentiles. Percentiles are like the 80th percentile, like we're seeing here. You would use the same procedure, inverse norm, 0.8 for the area, and something like that. All right, we started calling this same procedure is used to find critical values once we get to the later chapters. But it's the same thing. The critical values are inverse norm, norm.inv. When we use t critical values, it was inverse t, or t.inv. All right, to ensure that we have a bell curve for sample means, we want 30 or more. And then are there any exceptions to that? So if I had a sample of size 10, is there a way that could be bell-shaped? So yes, there are exceptions, and that's if the population is already normally distributed. If it's bell-shaped, then the distribution of sample means will be bell-shaped. It's like that lab we did where the salary of the NBA players is so extremely right-skewed. And when we start doing samples of size 30 even when we got to that number, this distribution of sample means was still right-skewed. And it's because the distribution of sample means follows its parent population distribution initially for small sample sizes. So if you are normally distributed to begin with, then the sample mean distribution will be normally distributed as well. So we'll already have a bell curve. All right, this question right here, this just gets at the heart of how do you make alterations when we're dealing with sample means versus the regular distribution. So this would be a DISTR normal CDF for probability. An individual has a height of 70 inches, above 70 inches. So that means the lower number is 70. The upper number is some large number, so I'll just pick a bunch of 9s. The mean is 66, and the standard deviation is 4. So there is my probability, 0.159 roughly. All right, but if I have a sample mean that I'm looking for the mean of, like what's the probability a sample mean of 16 individuals is above 70? Well, now it's the same procedure. It's 70 for the lower number, some big upper number, the mean, but now the standard deviation is 4 divided by the square root of the sample size. The sample size was 16, and I could write it that way, or I could just realize that square root of 16 is 4, and 4 divided by 4 is 1, and just put a 1 after that last comma. But either way, it's going to work. So this is 0.0, again, e negative 5. That's 0.00, 4 leading zeros, and then a 3. So this is much, much, much smaller of a probability to have a mean of 16 individuals be above 70. Are any of these considered unusual? Yes. The mean of 16 above 70 is very, very, very unusual. All right, 6.3, we studied the idea of point estimates and what are biased point estimators, what are unbiased point estimators. So the unbiased ones that we discovered in kind of the video that I put out there that shows you the proportion is unbiased, the mean Sample mean is an unbiased estimator, and the sample variance is unbiased. But like the median, the range, and the standard deviation were all biased estimators. This is not an exhaustive list, but those are just some of the ones that we saw that are biased versus unbiased. What does it mean to be biased? Unbiased estimators, they target the parameter that they estimate. And that means they're just as likely to be an overestimation as they are an underestimation. But the bias estimators, like for instance the standard deviation, it typically overestimates. It's typically when its estimations are more one-sided than the other. So that's what we mean by bias. There's a general trend to be above or below where they should be, and not an equally likely chance to be above or below. So those three that we studied in this course, the proportion, the mean, the variance, are our three unbiased estimators. What do we mean by a point estimate? We're talking about something we can get from a sample to estimate a parameter. So the best point estimate for a population mean is the sample mean, x bar. The point estimate for population proportion, which is p with a little hat on it. We call it p hat, and it is the sample proportion. And the point estimate for the population standard deviation is S, the sample standard deviation. All right, what do we use to estimate sample proportions? Well, we're going to use a normal distribution, which is sometimes referred to as the Z distribution, the standard normal distribution. The distribution of sample means, when we're talking about a practical use of estimating sample means, then we're going to follow a T distribution, which is a bell-shaped distribution, but it is also, it varies. It's sometimes wider and skinnier depending on your sample size. All right, and then the distribution of the sample standard deviation follows a chi-square distribution. It's supposed to be a Greek letter chi squared, but for whatever reason when I was typing this below, it wasn't cooperating. All right, be able to find the sample proportion, the margin of error. All right, if the initial interval is just A to B, a lower number and an upper number, the sample proportion is the number in the middle there, which would be A plus B over. That would be our sample proportion. That's the average of A and B. All right. And then if we want to do the margin of error, there's a couple ways to do it, but the easiest way is to take the upper number, subtract the lower number, and then divide by 2. That's our margin of error. All right, and then be able to find the critical values of the chi-square distribution. So I just pasted some videos showing you guys how to do that with the TI-83 and then a spreadsheet, how to find those critical chi-square values. All right, one, prop Z intervals do confidence intervals about prop proportions. All right, a T interval does confidence intervals for means, if you're doing that on the TI-83, 84. And the chi-square solver procedure, that I had some videos similar to the one you'd see here that will give you those chi-square confidence intervals. Those are for standard deviations. All right, this is a link to the formula sheet that you're allowed to use. Let me actually right-click it. This formula sheet, you are allowed to use this. You're going to have this available to you on the final. You just need to be able to use it. All right, so what I highlighted in there is if you need Z alpha over 2, you can use the formula. The formula sheet will show you that you need it, but you need to be able to figure out how to find it with technology. So if you have a 99% confidence interval for a proportion, well, 1 minus 0.99 is 0.01. 0.01 divided by 2, right? Alpha over 2, we're dividing, this is alpha. Confidence level subtracted from 1 is alpha. Dividing that by 2 is alpha over 2. So alpha over 2 is 0.005. And that's what I would use in inverse normal. 0.005, and then enter, and there's the number I need. So that's the number for that part. And then I could plug in the rest of the values, whatever P hat, Q hat are. I can plug that in there and use it. But inverse normal will find that. If I wanted to do the same thing with a spreadsheet, I would just have to type equals first, norm.inv, or just inv. Put in the area to the left of the number. So again, 0.005, and then comma. What's your mean? You can click on this little question mark to get the order. So what's your mean? comma, what's your standard deviation? All right, and then there's that number to 3 places. And if I wanted more places, I could click this and it will start to match up what I'm seeing here. So just know that your critical number that you find, you can find it with norm, INV, you can find it with the TI calculator. All right, same thing for T, there's inverse T. If it was for means and I had 99% confidence, let's just do a different number for the practice. 90% confidence. 1 minus the confidence level is 0.1 this time. I take that alpha, divide it by 2, I get 0.05, and that's what I need to plug in for T. All right, so 0.05. Now we would need to know like a sample size so we could get degrees of freedom. Let's say the sample size was 45. That would mean the degrees of freedom is 44, one less, and then we paste, and then there is our critical numbers, all right, for the T distribution. All right, and then you can, again, watch the videos up there that I posted about finding those critical values for chi-square. All right, there are some of those in the, I believe it was 7.3 videos that you can find those. All right, minimum sample size formulas. That is these right here, the chapter 7 formulas. And you typically see those used with proportions. So these two. So if P and Q are known, then you would use this and you would plug them in. If not, what you're doing is you're using the same formula, but you're doing 50-50. So 0.5 times 0.5 is 0.25. And so that's what you're using right here, is you're multiplying P hat and Q hat. It's just we're using 50-50 for those if we don't know them. That makes this N the biggest it needs to be. It basically maximizes N if we don't know P hat and Q hat. And that way we can guarantee that we've got a good enough sample size because we've made it as big as possible. All right, but let's just say, again, just for the practice, I want a estimate inside an error of 3%. So 0.03, that's my margin of error. Let's say my sample size was 30, and let's say that P hat is known to be, all right, so that's what I'm given. So I'm going to use this one. All right, P hat and Q hat are known. I'm not giving Q hat here, but remember Q hat is just 1 minus P hat. So 1 minus 0.4 is 0.6. And now I can plug all these numbers in to the calculator and use that formula. All right, so up top it's Z alpha over 2. Again, I would need to know the confidence level that we want. So let's say I wanted 95% confidence. That's that typical value for confidence. So we would need to do 1 minus 95%, 0.05. We're going to divide that by 2 to get the alpha over 2. And then that's the number I'm going to plug into inverse norm. 0.025, paste that in. So this negative 1.96, positive 1.96. That's my Z alpha over 2. So I'm going to do 1.96. I'm going to multiply that by P hat. All right, P hat was 0.4. Right, I also multiply it by Q hat. Q hat was times 0.6. And then I divide by the margin of error squared. So I'm going to do divide by, open parentheses, the margin of error was 0.03 squared, close those parentheses. All right, there's that 5.226 repeating. I'm going to round that up to 523. So my sample size, 523. All right, the next question in here says, make sure you always know you always must round that up. So even if that had been 522.3333 repeating, I would still round it up to 523 because we always round that calculation up. All right, there always must be some kind of equality in the null hypothesis. So equality in the null. Alternate hypothesis will always have one of those greater than, less than, or possibly not equal to. All right, so this is H0. This is either H1 or HA, just depending on the textbook or the author you're looking at. All right, these order symbols here, they are associated with the test type. So if it's a left tail test, we're using the less than symbol. Right tail test is a greater than symbol. Two-tailed is a not equal to. All right, be able to find test statistics. Again, that is these formulas here are the test statistics formulas. So if, let's say, P hat was 0.57, let's say P was equal to 49, and the sample size was 140, right? I would just grab my calculator, parentheses, because we got subtraction up top. P hat's 0.49, minus P is 0.57, close that parentheses, divide by, all right, the square root, second square root, and then this has a fraction in it, so we just multiply and divide. Now this is, this is, P hat was 0.49, P was 0.57, the way I've got the numerator written. So P is 0.57 times Q is 1 minus P. So you can actually do that separately and say that's 0.43 is Q. Or you can actually, even in the square root thing here, you could do 1 minus and then type in the P again. So it literally is that. So you can type it in as a formula, or you could, do the math separately. And then we divide that by the sample size. So there would be that critical value. All right, and just for practice, let's say the mean of a sample is 27.4, mu is 21.5, and let's say the standard deviation is 12.3, and the sample size is 36. So for that one, we would do, again, parentheses, because we got subtraction up top, 27.4, 21.5, close that parentheses, divide by. Now, what we're dividing by is a fraction, so we're going to put it in a parentheses. Numerator is 12.3, divided by the denominator has a square root, just like with the other one. The square root of the sample size. If you recognize that as a perfect square, we just wanted to put 6, that would be perfectly fine as well. So there's my critical T there to 8, to 2 decimal places. We typically round those to 2 places. All right, and then be able to find those critical values of test when you're given a significance level. So these are the test statistics that we just did, but the critical values are the numbers that these test statistics have to be larger than an absolute value, if they're negative, for them to be considered significant or for us to reject the null hypothesis. So with the critical Z values, I gave you a different video because my videos were always about that version of them from way back here at chapter 3 when we weren't really calling them critical values yet. So I put that video in there, but you can use that video in the procedures to find those critical values. And then I do it with a spreadsheet as well for normal distributions back in the early parts of chapter 6. All right, and then T values, those were specifically for this chapter, so I did refer to them as critical values. But in these earlier video, especially this one, the spreadsheet that I did, I'm just referring to them as missing numbers on a normal distribution, but that's what a critical value is. All right, be able to go through, this was all in chapter 7, be able to go through, chapter 8. Find the p-values for the different statistics. So a p-value for a test statistic for a t-test. P-value for a test statistics for a one prop z test. So anyway, just visually, what is a p-value? So you got your bell curve. It's either a z distribution or a t distribution, depending on if you're doing a mean or a proportion or a mean. And you found your test statistic. So your test statistic, I'm going to put TS, test statistic. It all depends on your alternate hypothesis. So if it said something like the mean is greater than, some number, then that means you're going from your test statistic into the tail, and you're using, normal CDF, or in this case, since it's a mean, TCDF, or if it was a proportion, if this wasn't mu, if it was P, then you would be using normal CDF because it's a normal distribution. But it's either normal CDF, TCDF if you're using a TI calculator, or the normal DIST or the TDIST if you are using a spreadsheet. All right, if you have a two-tailed test though, just don't forget, if it says not equal to, and this is where your test statistic falls, well, you also have to consider that there could have been that test statistic this far away in the other tail, and the p-value gets doubled, because what you're doing is you're finding the area in that upper tail wherever the test statistic fell, but you're also considering the opposite, so negative test statistic, the opposite of the test statistic in the lower tail and below the area below that. And vice versa, your test statistic could have been negative, and then you're changing it to a positive in that case and putting the area in both tails. So you always double the area that you get if you're doing specifically a two-tailed test. All right, if you reject the null hypothesis, then there is significant evidence in support of the alternate hypothesis. If you fail to reject the null, there is not significant evidence in support of the alternate. Okay, so rejection is because there is significant evidence. Failing to reject is because there is not significant evidence. Make sure you understand that. All right, in chapter 10, make sure you understand the bounds for R. R can be, the lowest R can be is -1, the highest it can be is +1, but those are both great numbers for R. The worst value it can be is 0, right in the middle. So the range on the number line is from -1 to +1. And this is, no correlation is in the middle. And then the further it goes to the right, there's more correlation, and it's positive correlation. And then this is perfect positive correlation. But if you go to the left, it's not getting less correlation from 0, it's more negative correlation in that region as we make our way to -1. Then we get to -1, we have perfect negative correlation. Right? That would be like the points line up perfectly in a straight line. All right. If it was negative but not perfect, then those points would fall as you go left to right, but not predictably, like they would kind of zigzag as they make their way. But they would be making their way lower as you go to the right if we have negative correlation. That's the reason why it's like the middle out. Like the middle is bad, and then as we make our way out further, 1 unit to left or right, we get better and better and better with our correlation measure. All right, I got several videos in chapter 10 showing you how to do all this stuff in either a spreadsheet or a TI. I strongly encourage you to use a TI in chapters really 7, 8, and 10. TI outperforms spreadsheets. But if you don't have a TI, sheets can do it. It's just you have to do a lot more by hand yourself with these formula sheets, right? But you can still do it. There's just some limitations that the TI doesn't have. All right, and then the big thing on prediction is that's not going to be just sitting there given to you on any of these sheets. Use the mean of the Y values for estimations when you do not have significant correlation. So if you do your correlation test, your correlation is kind of weak, like 0.4 and below, you got to kind of start looking at those correlation numbers to see, do I have significant correlation? And if you don't, then we predict with the mean, the average value of the Y coordinates. All right, just practice using these technologies. It's got to be a blank spreadsheet. You cannot sign into Google Sheets and open up any pre-existing. You got to be able to do these with a blank spreadsheet.